All right, I'm here with Kristen. She's going to help us work through this example of an orange being used to power a clock. So Kristen, these are the substances used to make this battery that is powering the clock. So what should I put in my list of substances to be oxidized or reduced?
So for the citric acid, it breaks up into H plus ions and citrate ions, which is C6H5O7 3-.
Very good.
And then water is a liquid, so it'll just be H2O. And then zinc and copper are both solids, so it'll be Zn and Cu.
Very good, very good. Next, we have to determine the substance that's easiest to oxidize and reduced. How are we going to do that?
Redox tables.
All right, so let's do oxidized first. Can you eliminate or kind of narrow down this list for what we might be looking for as substances to oxidize?
Metals will probably be the easiest to oxidize, so we should look for the zinc or the copper.
Why are metals so easy to oxidize?
They lose electrons easily.
They do. They do. So we're looking for zinc or copper, so we're going to scan along, and we don't have to scan too far. See it?
There's zinc.
There's zinc right there. So zinc is going to be oxidized. And there's the half reaction for that process with the voltage. So how do we do substance easiest to reduce?
Redox table again, just look for the first one.
Okay, reduction half reactions. This time we'll be looking for one of these substances, probably. Yeah. All right,
water, yeah.
So let's scan along here, see if you see anything. All right, why can't we use this reaction right here with the H plus in it?
It has H+, but it also has other ions, so we can't use it for this reaction.
Very good. We don't have NO3- in our list, so we can't use that one. There's lots of them that you can see on here, and that's why we haven't stopped on any of those. So, yeah, you can see it right there, correct?
Mm-hmm.
So that has H+ in our list. And so that's the H+ is being reduced, and there's the half reaction. All right. What's the first step for adding these two together, these half reactions together?
We'll have to cancel out the electrons, and since there's 2 electrons on each side, we don't have to do any multiplication.
Very nice. They just cancel, and we can just add these together. So we get zinc plus 2 hydrogens gives me zinc 2+ plus H2, and a positive voltage. And what's a positive voltage mean?
Spontaneous reaction.
Spontaneous reaction. That's why the battery's working and the clock's on. Very good. Thanks, Kristen. One high five. Yeah. All right, Josh is going to help me with this redox reaction, see if it's spontaneous. We're just going to see if the decomposition of water is spontaneous. So, Josh, I have 2 things that are supposed to be listed for things that could be oxidized or reduced. How am I going to fill in that table there?
Well, the only thing we have are the 2 water molecules, so it has to be 2 H2Os.
All righty, very good. So, substance easiest to oxidize and easiest to reduce. How are we going to figure that out?
We can use our redox table to find the half reactions.
All right, and since it's water, we're basically looking for the half reaction that only has water as a reactant. So on the oxidation side, scan through. Might have to scan for a while. All right. Okay. Why can't we use this one right here that has water in it?
Because it has stuff that we don't have. We only have water.
All right, so we don't have SO2 on our list. Correct, so we can't use that. So let's keep going. You'll see some other examples that have water in them, but here is the half reaction that has only water as a reactant. So that's the half reaction for the oxidation of water. So we can write that here on the line. So how do we determine the substance that is reduced?
We look at the other half of our redox table and look for the equation that has water as the only reactant.
Okay, so once again, you might see some half reactions that have water in them, but not water by itself. So you got to keep scanning and find the half reaction that has water just by itself. Eventually you get to it, and it's right here at negative 0.83 volts. So water is also going to be reduced. This is the half reaction for the reduction of water and the voltage. All right, so now that we have the half reactions, how are we going to add these together?
Well, since they both have 2 electrons in them, we don't have to multiply anything, and we can just cancel out the electrons right away.
Very good. When you add these together, you're going to get 3 waters plus a half oxygen plus H2 two H pluses and two OH minuses. So this can also be simplified. How can we simplify this?
Well, hydronium and hydroxide will just always spontaneously form water.
All right, so that means we have two water molecules over here. So then what will happen to the waters here and here? Oop.
They cancel out.
Okay, so then these waters are going to cancel. We're left with one H2O, half O2, and H2 gas, and it's a negative voltage. So first of all, let me make these all whole number coefficients in the reaction. What does a negative voltage tell you about this process?
That it's non-spontaneous.
Correct. The decomposition of water is non-spontaneous. Very good. Thanks, Josh. All right. So the decomposition of water is a non-spontaneous process. Water will not spontaneously break down into H2 gas and O2 gas. However, what I'm about to show you is if you put some electrical energy into this reaction, into the water, and supply this negative 1.65 volts, you can actually make this reaction spontaneous. This is the process of electrolysis. If you remember from when we talked about the models of the atom, electrolysis was a technique discovered in about the mid-1800s that allowed for the discovery of a lot of new elements. Remember, water was thought to be a pure element until a current was passed through it, and it was found that it would separate into two gases, hydrogen and oxygen. So I'm going to show this to you in this electrolysis setup. You can see here that we have a power supply hooked up to this electrolysis of water setup. You can see the two electrodes here, and there are bubbles of gas being formed at these two electrodes and collecting at the top. You'll notice on the left side that twice as much gas is being collected than compared to the right side. That means the electrode on the left is the cathode, because hydrogen gas is being produced at the cathode, and you produce twice as much hydrogen gas compared to oxygen gas. The electrode on the right is the anode, because oxygen is being formed there, and you make half as much oxygen gas in this process than hydrogen gas. So water can be made to decompose if you add an electrical current and perform electrolysis.